Part 4 of Unit 9 is about osmosis and other solution properties. Some substances form semi-permeable membranes that allow smaller particles to pass through them, but they block out other large particles. Osmosis is the movement of solvent particles through one of these semi-permeable membranes. The membrane stops the solute but allows the solvent to pass through it. In biological systems, most semi-permeable membranes allow water to pass through as the solvent, but the solutes are too large to pass through that semi-permeable membrane, so they don't move. So there's a net movement of solute from the area of higher solvent concentration to the area of lower solvent concentration. If you want to think about that in terms of the solvent's going to go from the area of low solute concentration to the area of high solute concentration. So if we look at this picture here, we've got a tube being divided by a semi-permeable membrane. On the left side we have a concentrated solution with a high amount of solute, and on the right side we have a dilute solution with a low amount of solute. What's going to happen is the water molecules, the solvent, is going to move from the dilute side to the concentrated side, and you would actually see a change in the water level inside this tube because the water is moving through the membrane to the more concentrated side. The solvent is moving towards the concentrated side to dilute it. Now, there is a certain pressure we can apply to the left side of that tube to stop that osmosis. That's called the osmotic pressure. Osmotic pressure is the pressure that's required to stop osmosis, and we can calculate it with this equation. Osmotic pressure is abbreviated pi because why not? And that's equal to mRT. So pi is the osmotic pressure, m is the molarity of the solution, R, that's our gas constant, 0.0821, and T is temperature in Kelvin. So to calculate the pressure required to stop osmosis through a semi-permeable membrane, you use this equation. If you ever find that two solutions have the same osmotic pressure, those are said to be isotonic. We can apply an easy example of osmosis to blood cells. If the solute concentration outside the cell is greater than the concentration inside the cell, that solution is called hypertonic. And what's going to happen is the solvent, the water, is going to flow out of the cell to the area of high solute concentration, and that's actually going to cause the cell to get crushed because of that high osmotic pressure outside the cell. Now, if the opposite is going on, if the solute concentration outside the cell is less than the concentration inside the cell, it's called a hypotonic solution. Now, if there's a high solute concentration inside the cell, the solvent, or water, is going to flow through the semi-permeable membrane around the cell into the cell, and if that happens too much, the cell can actually burst because of the high amount of solvent flowing into the cell. Some other types of solutions that you need to know about. A solution is called a suspension if it's a heterogeneous mixture that has particles large enough to settle to the bottom of a container. So if the particles are not fully dissolved and visible like in a solution, if you leave a container alone and don't stir it, you'll actually see the particles settle out to the bottom. It's called a suspension. If you stir it enough, the particles become suspended throughout the solvent, so that's where the name comes from. Colloids are heterogeneous mixtures of particles that are larger than individual ions or molecules, but they're too small to be settled out by gravity. So suspensions have the largest solute particles. Those will actually settle out to the bottom of a container. Colloids have the next smallest size of solute particles. They're not going to settle out to the bottom of a container, and you may not be able to see them. And solutions are just tiny molecules or ions that are dissolved throughout the solvent, and you can't actually see them. The way to tell colloids and solutions apart is to use the Tyndall effect. In the Tyndall effect, if you shoot a beam of light or a laser through a colloid, those particles are large enough to scatter the light, and you'll actually be able to see that beam of light. So in this picture, we've got a solution on the left with tiny particles that don't scatter the beam of light, and a colloid is on the right. The particles in that are large enough that they scatter the beam of light, and you can actually see it as it's passing through that container. Your question for this section: what is the concentration of sodium chloride in water needed to produce an aqueous solution isotonic with blood? The osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius.